Now we shall briefly delve into the realms of mathematics explored in the modern era, with a deliberate omission of current-day computer science, thus only covering the 19th and early 20th century of mathematical blossoming. First, we shall dwell on one of the three unmatched in mathematical history: Archimedes, Newton, and now Carl Friedrich Gauss. Gauss, like many other mathematicians in the list of the greats, was a child prodigy, whose genius was very nearly robbed from the world by his father, who wished for him to have nothing to do with mathematics. And with his greatness came many, many mathematical myths, the most famous of which involving the addition of numbers in an arithmetic series, which goes as such. Find the sum of the first 100 integers, 1 plus 2 plus 3 plus all the way to 100. Before the instructor could finish the problem, Gauss had written a single number on his slate, which turned out to be correct: 50,500. Unsatisfied by the lack of rigor in many of the proofs of previous mathematicians, Gauss became the first of what may be called a rigorist, and set himself the task of, among other things, filling the gaps of the theory of numbers. It would be impossible to recount only a fraction of Gauss's great work, so I'll only introduce his works on quadratic reciprocity and modular arithmetic. To begin, the modulo operator, written mod, practically equates remainders, such that a is equal to b mod m, where the remainder of a divided by m is equal to b divided by m. Now, let x denote an unknown number, r and m given numbers, of which r is not divisible by m. Is there a number x such that x squared is equal to r mod m? If so, then r is a quadratic residue of m. If not, a quadratic non-residue of m. For the given m, what are the quadratic residues and non-residues of m? Simplified to primes, pq, Gauss provided 6 distinct proofs of a beautiful quadratic reciprocity between pairs of solutions. It asks, x squared is equal to q mod p, then x squared is equal to p mod q, where p and q are primes. And both congruences are both either solvable, where you can find at least one x, or unsolvable, you can't. Proving this baffled the prolific Euler. Now come the geometrical revolutions of Nikolai Lobachevsky and Bernhard Riemann, the former named the Copernicus of geometry, joined by, of course, Gauss in his curiosity over the geometry of Euclid, which dominated for over 2 millennia. Lobachevsky challenged an axiom, the fifth of the elements postulates, which asserts that, given line L, there is only one line L' through a point P not on the L, which is parallel to L, i.e. L' and L never meet. However, this was shown not to be true on all surfaces. For example, on a Euclidean plane, the angles of a triangle add up to 2 right angles. However, on a perfect sphere, the angles add up to multiple values greater than such, and on a trumpet-like shape called a tractrix, the angles add up to less. Bernhard Riemann would come into the scene and build the foundations of topology with his Riemannian surfaces, the study of the properties of a geometric object under continuous deformation. Furthermore, Riemannian geometry managed to extend differential geometry to n dimensions, and to contribute to the generalization and despecialization that is non-Euclidean geometry. His work is still being researched and of tremendous use today. The mathematicians William Rowan Hamilton and George Boole are 2 of the greats who revolutionized algebra. Hamilton is seen as one of the founders of modern linear algebra, for example, discovering the algebra of quaternions. This was a way of extending complex numbers and thereby ditching the commutative law. Boole's work is seen as the foundation of modern-day information technology. His Boolean algebra, introduced in his book Laws of Thought, is the logic used in computers, with values of true and false, ones and zeros. It is thus the area of mathematics that deals with the logical operations, ist, and, or, not, etc. Two tragedies deeply linked in mathematics were Niels Henrik Abel and Évariste Galois, the former dying of tuberculosis 2 days before being appointed to a professorship at age 26, and the latter shot dead on the field of honor at age 20. Mathematics is owed of these young geniuses the theory of groups and abstract algebra, concerned with radical roots of higher degree equations. Now, in the last few minutes, I've quickly fired off a small fraction of the prominent mathematicians of the 19th century, which have produced new fields of epoch-making mathematics: Gauss's rigor, non-Euclidean geometry, modern-day algebra, and the theory of groups, just to name a few. Further, entirely new fields were created in the early 20th century, such as the following: differential geometry, which became important on the eve of Einstein's theory of relativity; mathematical logic, especially concerning the foundations of modern mathematics, of which I will tell a tale next time; topology, which was brought into mainstream mathematics under the light of Henri Poincaré, who collected and greatly advanced the field; and John von Neumann's game theory, which greatly advanced knowledge of the social sciences and rational agents, making them rigorous and mathematical. Other notable figures in the wake of the 20th century include Srinivasa Ramanujan, an Indian mathematician who proved over 3,000 theorems and provided the mathematical world with many beautiful formulae; Paul Erdos, the most prolific mathematician, matched only by Euler, who wrote over 1,500 papers with more than 500 collaborators. The joke Edder's number has been used to determine how many degrees of separation an author is from collaborating with him. And Emmy Noether, considered the most important woman in mathematics, including theories of rings, fields, and algebras. Now, as I close this section of modern mathematics, as we enter an epoch just as radical and as young as perhaps that of Descartes' geometry, or possibly one greater, and as it has spread so fruitfully as a field, we see the trend of mathematics as one of constant evolution. Yet now progress is so rapid, it is rather a story of constant revolution. Georg Cantor analyzed the infinite, which has produced a schism in mathematics, from which various fields have emerged and asserted themselves as essential.